Somewhere in the universe, there's a galaxy so violent, so extreme, that scientists have given it a chilling nickname: the most horrific galaxy. Black holes devouring stars, radiation blasting through space, and chaos on a scale we can barely comprehend. Today, we're uncovering what makes this galaxy so terrifying. The most horrific galaxy. A galaxy exists where stars do not simply live out their quiet, predictable lifetimes, but are instead torn apart, compressed, ignited and destroyed in a relentless cycle that never seems to slow down. A place where the very building blocks of solar systems are caught in forces so extreme that stability becomes impossible and destruction becomes routine, where radiation floods through space at such intensity that entire planetary systems would be wiped clean before they even had time to react. Their atmospheres stripped away as if they never mattered. Their surfaces blasted with energy so powerful that no chemistry, no biology, no structure could survive. A place where the idea of a calm orbit or a stable sky simply does not exist. If Earth were somehow placed inside this galaxy, there would be no warning and no gradual change, because the moment it arrived, the process would already be underway. The upper layers of the atmosphere would begin to peel away under the pressure of high-energy radiation and particle storms. The protective magnetic field would be overwhelmed by charged particles moving at incredible speeds, and within moments, the delicate balance that allows life to exist would collapse completely as ultraviolet and X-ray radiation would penetrate straight to the surface, breaking apart molecules, shattering chemical bonds, and destroying DNA faster than it could ever repair itself, meaning that every living thing, from the smallest microorganism to the largest organism, would be erased not over centuries or years, but in seconds, leaving behind a lifeless, exposed world, drifting in a storm of energy it could never survive. The oceans would not boil in a dramatic explosion, nor would continents crack apart in a cinematic collapse, because the real horror here is quieter and far more absolute, as the very conditions required for life would simply cease to exist, replaced by an environment so hostile that even the idea of recovery becomes meaningless, since there would be no shelter, no safe region, no moment of calm, only a continuous bombardment of energy and matter that ensures nothing stable can ever form, let alone endure. And this isn't fiction. This galaxy exists. What you're about to see is not an imagined nightmare created for storytelling, but a real object in the universe that astronomers have studied for decades. A galaxy that has forced scientists to rethink how violent and unstable these massive systems can become under the right conditions, and one that continues to challenge our understanding of how stars are born, how they die, and what happens when those processes are pushed to their absolute limits. This galaxy is known as Messier 82, a name that might sound neutral or even ordinary at first, but one that hides an environment so extreme that scientists often describe it using words that are rarely applied in astronomy. Words like violent, chaotic, and even horrific. Not because they are trying to exaggerate its nature, but because the processes taking place inside it are genuinely unlike what we see in calmer, more stable galaxies like our own. Messier 82 sits roughly 12 million light-years away from Earth, which in cosmic terms places it relatively close to us, close enough that we can observe it in detail with modern instruments, yet far enough that what we see today is actually a glimpse into its past, a snapshot of events that unfolded millions of years ago. And even in that snapshot, the signs of extreme activity are impossible to ignore, as the galaxy shines with an intensity that does not match its size, glowing brightly in wavelengths of light that reveal processes hidden from ordinary observation. Scientists refer to Messier 82 as a starburst galaxy, a term that might sound technical but describes something very specific and very unusual. Because in most galaxies, including the Milky Way, stars form at a relatively steady and controlled rate, with gas clouds slowly collapsing under gravity to create new stars over long periods of time. But in a starburst galaxy, that process is accelerated to an extraordinary degree, with stars forming at rates 10, 20, or even 100 times higher than normal, turning the galaxy into a kind of cosmic furnace, where creation happens so rapidly that it begins to trigger destruction just as quickly. At the same time, Messier 82 is known for something even more dramatic, something called a galactic superwind, which refers to enormous streams of gas and particles being blasted out of the galaxy's core at incredible speeds, driven by the combined energy of countless exploding stars and intense stellar radiation, creating vast outflows that extend far beyond the galaxy itself, carrying with them the material that would otherwise form future stars and reshaping the galaxy from the inside out. These two features alone, the starburst and the superwind, are enough to make Messier 82 stand out among thousands of known galaxies. But they also raise a fundamental question that scientists have been trying to answer for years. Because while we know what is happening inside this galaxy, understanding why it is happening at such an extreme level requires us to look deeper into its history, its structure, and the forces that have shaped it into what it is today. What makes this galaxy so destructive compared to others? To answer that question, we have to go back to the moment it was first noticed, long before modern telescopes, space observatories, and before scientists had any idea that such violent processes could even exist on a galactic scale. The discovery of Messier 82. In the year 1774, at a time when the night sky was still being mapped piece by piece by astronomers using relatively simple instruments compared to what exists today, a German astronomer named Johann Ellerat Bode pointed his telescope toward a region of the sky that had already been observed many times before, a region filled with stars that were familiar to observers and part of a well-known pattern called Ursa Major. And within that familiar patch of sky, he noticed something that did not behave like a normal star, something faint and slightly stretched, a dim patch of light that seemed to glow softly without the sharp clarity that stars usually have when viewed through a telescope. At that time, the understanding of the universe was very different from what it is today, because astronomers did not yet fully grasp the idea that there were entire galaxies beyond the Milky Way, and many faint objects in the sky were simply grouped together under the term nebula, which was used to describe anything that appeared cloudy, diffuse, or unclear. So when Bode recorded what he saw, he did not identify it as a galaxy filled with billions of stars undergoing extreme physical processes, but rather as a faint nebula, a small and somewhat unremarkable object that did not immediately stand out as something extraordinary. The telescope he used would have shown only a limited amount of detail, because 18th century optical instruments were restricted to visible light and had much lower resolution than modern telescopes, meaning that what he saw was essentially a blurred and dim shape, without any clear internal structure. And under those conditions, there was no reason to suspect that this object was anything more than a distant, faint cloud of material quietly existing in the vastness of space without drawing attention to itself. The object would later be catalogued as Messier 82, but at the moment of its discovery, it did not carry that name or that significance, because it was just one of many entries in a growing list of faint celestial objects that astronomers were documenting, and it would take many decades of observation along with major advances in technology before its true nature began to emerge. Its position in the sky within Ursa Major made it relatively easy to locate for astronomers who knew where to look, since this constellation contains some of the most recognizable stars in the Northern Hemisphere, forming patterns that have been used for navigation and observation for centuries. And because of that, Messier 82 remained visible and accessible to observers over time, even if they did not yet understand what they were looking at. And even though it appeared faint, it was close enough in cosmic terms to be studied in increasing detail as telescopes improved. The distance to this object, which we now know to be about 12 million light-years from Earth, adds another layer to the story, because that distance means the light reaching us today left the galaxy 12 million years ago, long before humans existed in their current form, long before modern civilizations, and even before many of the geological changes that shaped Earth as we know it, meaning that every observation made of this galaxy is actually a look into its past, a delayed signal that carries information about conditions that existed millions of years ago. At the time of its discovery, however, this distance was not known, because measuring distances to objects beyond our own galaxy was an enormous challenge that would not be solved until much later. So Messier 82 remained a mystery not only in terms of its structure and behavior, but also in terms of how far away it actually was. And without that context, it was impossible to fully understand its scale or significance. As the years passed and astronomy began to develop more precise tools and methods, observers started to revisit objects like Messier 82 with better equipment. And one of the first changes that became noticeable was its shape, which appeared more elongated than previously thought, stretching out in a way that distinguished it from rounder or more diffuse nebulae, giving it a form that looked narrow and extended, almost like a thin beam of light, which led to the nickname the Cigar Galaxy, a name that reflects its distinctive appearance when viewed through improved optical telescopes. This elongated shape was not just a visual curiosity, but an important clue, because it suggested that the object had a structure that was more complex than a simple cloud of gas, hinting at the possibility that it might be a system with internal organization, perhaps even something similar to the Milky Way, although that idea was still not fully accepted at the time, as the concept of galaxies as separate systems was still being debated and refined. Optical telescopes, which rely on visible light, continued to provide clearer and sharper images as technology advanced, revealing more detail in the structure of Messier 82, including variations in brightness and the presence of dark regions that appeared to cut across its length, which were later understood to be dense clouds of dust blocking light from behind them, creating patterns that hinted at internal activity and complexity. However, even with these improvements, optical observation alone could not reveal the full story, because a significant portion of what was happening inside Messier 82 was hidden behind thick layers of dust and gas that absorbed visible light, effectively masking the most energetic and dynamic processes from direct view. And this limitation meant that for a long time, astronomers were only seeing the surface of the galaxy's behavior, without access to the deeper and more intense activity taking place within. The situation began to change with the development of radio astronomy, which allowed scientists to detect signals at wavelengths much longer than visible light, enabling them to peer through the dust that obscured the galaxy's interior and detect emissions associated with energetic processes, such as the remnants of exploded stars and the movement of charged particles, providing the first real indication that Messier 82 was far more active than it appeared in optical images. Radio observations revealed that the galaxy was emitting strong signals that could not be explained by a calm or inactive system, suggesting that something inside it was generating large amounts of energy. And these findings began to shift the perception of Messier 82 from a quiet, faint object to one that might be undergoing significant internal changes, although the full extent of those changes was still not clear. The introduction of infrared astronomy marked another major step forward in understanding this galaxy, because infrared light can pass through dust more easily than visible light, allowing astronomers to observe regions that were previously hidden and detect heat emitted by objects and processes that do not produce much visible light, such as newly forming stars and dense, warm gas clouds. When Messier 82 was observed in infrared wavelengths, the results were striking, as the galaxy appeared much brighter than expected, indicating that it was producing large amounts of heat and energy, far beyond what would be typical for a galaxy of its size. And this excess energy pointed directly to intense star formation activity, with massive stars being created at a rapid rate within the galaxy's core. These observations revealed that what had once been classified as a faint nebula was actually a highly active system, with processes occurring at a scale and intensity that were not immediately visible through traditional methods, and the contrast between its calm optical appearance and its energetic infrared signature highlighted the importance of using multiple wavelengths to study astronomical objects, as relying on visible light alone can lead to incomplete or misleading conclusions. As more data was gathered from both radio and infrared observations, along with improvements in optical imaging, a clearer picture of Messier 82 began to form, showing a galaxy that was not only forming stars at an unusually high rate, but also experiencing frequent and powerful events that released enormous amounts of energy into its surroundings, shaping its structure and driving material outward in ways that were not seen in more stable galaxies. The presence of dense dust clouds, which initially obscured the galaxy's interior, turned out to be a key part of its behavior, as these clouds provided the raw material for star formation while also trapping heat and radiation, creating an environment where energy could build up and be released in bursts, contributing to the overall intensity of the system and making it one of the most active regions of star formation observed in the nearby universe. Over time, the classification of Messier 82 shifted from that of a simple nebula to that of a starburst galaxy, a term used to describe galaxies undergoing exceptionally high rates of star formation. And this reclassification reflected a deeper understanding of its nature based on evidence gathered across multiple wavelengths and supported by observations of its structure, energy output, and dynamic behavior. The evolution of our understanding of this galaxy, from a faint and unremarkable object to one recognized as one of the most active and intense galaxies known, illustrates how advances in technology and observation can transform our perception of the universe, revealing layers of complexity that are not immediately visible and uncovering processes that challenge our assumptions about how galaxies form and evolve. Each stage of observation added new pieces to the puzzle, from the initial detection of a faint glow in the sky to the recognition of its elongated shape, to the discovery of hidden activity through radio and infrared signals, and finally to the realization that this galaxy is undergoing processes that push the limits of what is typically observed in galactic systems, driven by conditions that create both rapid formation and rapid destruction on a massive scale. Even now, observations continue to refine our understanding of Messier 82, as new instruments and techniques allow scientists to study it in greater detail, examining the interactions between gas, dust, stars, and energy within the galaxy, and exploring how these elements combine to produce the extreme environment that defines it, an environment that was completely invisible to the astronomers who first recorded its existence over 2 centuries ago. What began as a faint, unclear patch of light has become one of the most studied examples of intense galactic activity, not because it changed over time in a way that made it more dramatic, but because our ability to observe and interpret it improved, allowing us to see beyond the surface and recognize the powerful forces at work within it. Forces that were always there but hidden behind layers of dust and limited by the tools available at the time. First signs something was wrong. For a long time, this galaxy did not immediately reveal how extreme it really was, because when astronomers first looked at it using optical telescopes, it did not explode with obvious chaos or dramatic features that would instantly signal danger or instability, and instead it appeared as a stretched, glowing shape that seemed quiet on the surface, which made the early stages of its study somewhat misleading, since nothing in those first images clearly showed just how much energy was being produced inside it, or how unusual its behavior truly was, compared to other galaxies of similar size. The first real sign that something was not normal came from a detail that might seem simple at first, but became more and more difficult to ignore as measurements improved, and that was its brightness, because Messier 82 appeared far brighter than it should have been when compared to other galaxies that were roughly the same size and structure. And this was not just a small difference that could be explained away by measurement errors or minor variations, but a consistent pattern that suggested something inside the galaxy was producing far more energy than expected. Brightness in astronomy is not just about how something looks to the eye, but about how much energy it is actually releasing across different wavelengths of light. And when astronomers began to compare Messier 82 to more stable galaxies, they noticed that it was emitting an unusual amount of energy, especially when considering its relatively compact structure, because larger galaxies with more stars typically produce more light. Yet here was a smaller system shining with an intensity that did not match its size. At first, this raised questions about whether the measurements were accurate, or if there were factors affecting how the light was being observed, because in astronomy, distance, dust, and angle can all influence how bright an object appears. But as more observations were made using different instruments and techniques, the pattern remained consistent, and it became clear that the brightness was not an illusion or a simple observational error, but a real characteristic of the galaxy. This led to a deeper investigation into where that energy was coming from, because brightness alone does not explain the source of energy. And to understand that, astronomers needed to look beyond visible light and examine other parts of the electromagnetic spectrum, which is where things started to become much more unusual and much more revealing. When Messier 82 was observed using infrared instruments, the results were striking in a way that could not be ignored, because instead of showing a moderate level of heat and energy, the galaxy was glowing intensely in infrared wavelengths which are associated with heat and the presence of warm dust and gas, and this level of infrared radiation was far higher than what would normally be expected from a galaxy of its size. Infrared radiation is especially useful in astronomy because it can pass through dust that blocks visible light, allowing scientists to see regions that are otherwise hidden. And in the case of Messier 82, those observations revealed that the galaxy was not just bright on the surface, but was filled with activity that was generating enormous amounts of heat from within, suggesting that something powerful was happening in its core and throughout its structure. The amount of infrared radiation being emitted indicated that there were large quantities of dust being heated to high temperatures, and this heating could not occur without a strong source of energy, which pointed directly to processes involving stars, because stars are the primary sources of energy in galaxies, especially young and massive ones that burn hot and release large amounts of radiation. This discovery shifted the focus of research towards star formation, because one of the most common reasons for high infrared output in galaxies is the presence of newly forming stars, which heat the surrounding dust and cause it to glow in infrared light. And when astronomers began to analyze the data more closely, they realized that Messier 82 was not just forming stars, but was doing so at an unusually high rate. The rate at which stars form in a galaxy is a key measure of its activity. And in most galaxies, this process happens at a steady pace, with new stars being created gradually over long periods of time. But in Messier 82, the data suggested something very different, because the number of new stars being formed was far higher than expected, and not just slightly higher, but dramatically higher, indicating that the galaxy was undergoing a phase of intense star formation. This was one of the most important turning points in understanding the galaxy, because it provided a direct explanation for both its unusual brightness and its strong infrared emissions, as both could be linked to the presence of large numbers of young, hot stars that were producing energy and heating the surrounding material. But at the same time, it introduced a new and more complex problem that was not easy to explain. The problem was not simply that the galaxy was forming many stars, but that it was forming them at a rate that did not match its size, because smaller galaxies generally have less gas available for star formation, and therefore produce fewer stars over time, while larger galaxies have more material and can sustain higher rates of star formation. Yet Messier 82 seemed to break this pattern completely, behaving like a much larger system despite its relatively modest size. This mismatch between size and activity created confusion among astronomers, because it suggested that there were factors at play that were not yet understood, something that was driving the galaxy to produce stars at a rate that went far beyond what its structure and mass would normally allow. And this raised fundamental questions about how star formation works under extreme conditions. At this stage, scientists began to compare Messier 82 more carefully with other galaxies, looking for similarities and differences that might explain its behavior. And while there were other galaxies known to have active star-forming regions, very few showed the same level of intensity across such a large portion of their structure, which made Messier 82 stand out even more as an unusual and important case. The high rate of star formation also had other consequences that added to the sense that something was not right, because massive stars, which form quickly in such environments, have very short lifespans and end their lives in powerful explosions known as supernovae, meaning that a galaxy producing many massive stars would also experience frequent and energetic stellar explosions, releasing even more energy into the surrounding space. Although this stage of research was focused mainly on the discovery of high star formation rates, the implications were already becoming clear, because a system that creates stars at such a rapid pace would also be constantly dealing with the effects of those stars' deaths, leading to a cycle of creation and destruction that could drive further changes in the galaxy's structure and behavior. The early confusion about why such a small galaxy was producing so many stars was not just a minor question, but a central problem that needed to be solved in order to understand the galaxy as a whole. Because without identifying the cause of this extreme activity, it was impossible to fully explain its brightness, its infrared emissions, or its overall dynamics. At this point, astronomers began to consider different possibilities, including whether the galaxy might have an unusually large amount of gas compared to its size, or whether there might be external forces influencing it, such as interactions with nearby galaxies. But these ideas required further investigation and more detailed observations before any conclusions could be drawn. What made the situation more complex was that the galaxy did not show obvious signs of the kind of large-scale disruptions that are sometimes associated with extreme star formation, such as major structural distortions visible in optical images, which meant that whatever was causing the high star formation rate was either hidden from view or operating in a way that was not immediately visible through traditional observation methods. The combination of unusual brightness, strong infrared radiation, and high star formation rates created a picture of a galaxy that was far more active than it appeared on the surface. And each new observation added to the sense that Messier 82 was not following the typical pattern seen in other galaxies, but was instead operating under conditions that pushed it into a different category altogether. As more data was collected, the evidence continued to point in the same direction, reinforcing the idea that this galaxy was undergoing a phase of intense activity that could not be explained by simple models of star formation, and that understanding it would require a deeper look at the forces shaping its environment and the processes driving its behavior. The early signs that something was wrong were not dramatic in the sense of a single event or a sudden change, but rather a series of observations that gradually built up a case, each one adding a piece to the puzzle and making it harder to ignore the fact that this galaxy was fundamentally different from what astronomers expected, and that difference was not just a matter of degree, but of kind. By the time these signs were fully recognized, Messier 82 had already moved from being a faint and unremarkable object to one of the most interesting and puzzling galaxies in the nearby universe. Not because it was larger or closer than others, but because it challenged the assumptions that astronomers had about how galaxies behave, especially when it came to the relationship between size, structure, and star formation. The question that remained was not whether something unusual was happening, but what exactly was causing it, and how all these observed features, brightness, infrared radiation, and rapid star formation, were connected, because answering that question would not only explain the behavior of this single galaxy, but also provide insight into how galaxies can evolve under extreme conditions, revealing processes that might have been more common in the early universe, but are rarely seen today. What is a starburst galaxy? When scientists describe a galaxy as a starburst galaxy, they are not using a dramatic word for effect, but are instead pointing to a very specific and measurable condition inside that system. A condition where stars are being formed at a rate that is far beyond what is considered normal for most galaxies. And to understand what that really means, it helps to start with how star formation usually works in a typical galaxy. Because without that baseline, the scale of what is happening inside a starburst galaxy, like Messier 82, cannot be fully understood. In most galaxies, star formation is a steady and controlled process that takes place over very long periods of time, where clouds of gas slowly come together under the influence of gravity, gradually becoming denser until parts of those clouds collapse inward and form new stars. And this process is not chaotic or explosive in the sense of happening all at once, but instead unfolds in a balanced way, with new stars forming while older ones continue their life cycles, creating a system that remains stable over millions or even billions of years. A key way scientists measure how active a galaxy is in terms of star formation is by looking at its star formation rate, which simply refers to how many new stars are being created within that galaxy over a given period of time, usually measured in years. And for a normal galaxy, this rate tends to fall within a relatively narrow range, depending on its size, the amount of gas it contains, and its overall structure. For example, in our own galaxy, the Milky Way, the star formation rate is estimated to be about 1 to 2 new stars per year, which might seem like a large number at first, but when spread across the entire galaxy, which contains hundreds of billions of stars, it actually represents a slow and steady pace, one that allows the galaxy to maintain its structure without exhausting its supply of gas too quickly. This steady pace is what keeps most galaxies in a kind of long-term balance, where star formation continues without overwhelming the system, and where the energy released by stars, including radiation and stellar winds, is not enough to disrupt the overall stability of the galaxy, meaning that while there is always activity taking place, it does not reach levels that would be considered extreme or unusual. A starburst galaxy, however, breaks away from this pattern in a very clear and measurable way, because its star formation rate is not just slightly higher than normal, but dramatically higher, often ranging from 10 times to even 100 times the rate seen in more typical galaxies. And this increase is not limited to a small region or a short period, but can affect large portions of the galaxy and continue for extended periods of time. In the case of Messier 82, observations have shown that it can produce up to 10 new stars per year, which might not sound like a massive number when compared directly to the Milky Way. But the key difference lies in the size and structure of the galaxy, because Messier 82 is smaller and more compact, meaning that this level of star formation is concentrated into a much tighter space, creating conditions that are far more intense than what we experience in our own galaxy. To understand why this difference matters, it is important to consider how star formation depends on the availability and behavior of gas within a galaxy. Because stars are formed from clouds of gas, primarily hydrogen, that must reach a certain level of density before they can collapse under gravity and ignite nuclear fusion. And in a normal galaxy, this process is limited by how much gas is available and how it is distributed, which naturally keeps the star formation rate within a certain range. In a starburst galaxy, something changes this balance by increasing the density of gas in certain regions, often in the central parts of the galaxy, where large amounts of material are pulled together and compressed, creating conditions where many stars can begin forming at the same time, rather than gradually and independently across different areas. Gas density plays a central role in this process, because the denser the gas becomes, the stronger the gravitational forces acting within it, and the more likely it is to collapse into smaller regions that can form stars. And when large volumes of gas are brought into a confined space, the number of these collapsing regions increases rapidly, leading to a surge in star formation that can spread across the galaxy. This increase in gas density does not happen on its own without a cause, because in order for gas to become so concentrated, it must be pushed or pulled into that state by external or internal forces. And one of the most important mechanisms behind this is the compression of molecular clouds, which are large, cold regions of gas where stars are born. Molecular clouds are normally stable structures, held together by a balance between gravity pulling inward and internal pressure pushing outward. And under typical conditions, only small parts of these clouds collapse at any given time to form stars. But when an external force compresses these clouds, it can disrupt that balance and trigger widespread collapse across multiple regions simultaneously. This compression can occur in several ways, but the key idea is that the gas is being forced into a smaller volume, increasing its density and making it much more likely to collapse under its own gravity. And once this process begins, it can quickly lead to the formation of many stars in a short period of time, as multiple regions within the cloud reach the critical conditions needed for star formation at nearly the same time. In Messier 82, the compression of molecular clouds has reached a level where it is not just triggering isolated bursts of star formation, but driving a continuous and widespread process that affects much of the galaxy, creating an environment where new stars are constantly being formed in large numbers, far exceeding what would be expected under normal conditions. As these stars form, especially the more massive ones, they begin to release large amounts of energy in the form of radiation and stellar winds, which interact with the surrounding gas and dust, heating it and sometimes pushing it outward, adding another layer of complexity to the system, because the very process of creating stars begins to influence the environment in which new stars are being formed. This creates a feedback effect, where the energy from newly formed stars can both trigger further star formation by compressing nearby gas and also limit it by dispersing material, depending on the conditions. And in a starburst galaxy, this balance tends to favour continued activity, at least for a certain period of time, allowing the high rate of star formation to be sustained. The result is a galaxy that is not just forming stars at a faster rate, but is doing so in a way that fundamentally changes its structure and behaviour, as the concentration of energy and matter in certain regions leads to conditions that are far more extreme than those found in more stable galaxies. When comparing Messier 82 to the Milky Way, the difference becomes even more clear, because while the Milky Way spreads its star formation across a large disk, with different regions contributing gradually over time, Messier 82 concentrates much of its activity into a smaller area, particularly in its central regions, where gas density is highest and conditions are most favourable for rapid star formation. This concentration means that the effects of star formation are also more intense, as the energy released by many stars in close proximity adds up, creating an environment where radiation levels, temperatures, and particle activity are all significantly elevated compared to what would be found in a more evenly distributed system. The idea of a starburst galaxy, therefore, is not just about producing more stars, but about how and where those stars are being formed, because the concentration of activity plays a crucial role in determining the overall impact on the galaxy. And in the case of Messier 82, that concentration is what drives many of the extreme conditions observed. As scientists studied these features in more detail, it became clear that the high star formation rate was not a temporary fluctuation or a small-scale event, but a defining characteristic of the galaxy during this phase of its evolution, one that influences everything from its brightness and radiation output to its structure and long-term development. The term starburst itself reflects this idea of rapid and intense activity, suggesting a sudden increase in star formation that stands out from the normal background level. And while the process can last for millions of years, which is long on human timescales, it is relatively short in the life of a galaxy, making it a distinct and important phase that can have lasting effects. Understanding what a starburst galaxy is requires looking beyond simple definitions and considering the underlying processes that drive it, including the role of gas density, the compression of molecular clouds, and the feedback from newly formed stars, all of which combine to create an environment where star formation is not just active, but accelerated to an extreme degree. In Messier 82, these processes have come together in a way that pushes the galaxy far beyond the typical range of behaviour, creating a system where the formation of stars is happening at a pace and intensity that sets it apart from most other galaxies, and where the consequences of that activity are visible across multiple wavelengths, from infrared to radio, revealing the full extent of what is taking place. This is what defines a starburst galaxy in practical terms, not just a higher number of stars being formed, but a set of conditions that allow that formation to happen on a much larger scale and at a much faster rate than normal, driven by changes in the distribution and behaviour of gas within the galaxy. But even with all of this, describing it as rapid creation only tells part of the story, because the same processes that drive this intense star formation also lead to effects that go far beyond simply producing new stars, effects that begin to reshape the galaxy and introduce levels of energy and instability that are not present in more stable systems. Because when stars form this quickly, especially massive ones, they do not remain stable for long, and their short lifespans lead to powerful events that release enormous amounts of energy back into the galaxy, interacting with the surrounding gas and dust in ways that can amplify the conditions that created them in the first place. And this is where the nature of a starburst galaxy begins to shift from being a place of rapid creation to something far more extreme, because the processes that make it so efficient at forming stars also set the stage for intense and continuous disruption, turning what might seem like a productive phase into one that carries the potential for large-scale change and instability. But this isn't just rapid creation, it's catastrophic. The trigger: galactic collision. For a long time, the extreme behaviour seen inside Messier 82 raised a very direct question that could not be ignored, because even though its high star formation rate and intense energy output were clearly measured and confirmed, those observations did not explain what had pushed the galaxy into such an unusual state in the first place. And without identifying a trigger, there was no clear way to understand why this galaxy, out of so many others, had become so active while many similar systems remained relatively calm and stable over long periods of time. The answer to that question begins with another galaxy located very close to it in space, a much larger system known as Messier 81, which shares the same region of the sky and is part of the same group of galaxies, meaning that these two systems are not isolated from each other, but instead exist within a shared gravitational environment, where their movements and positions influence one another over millions of years. Galaxies are not fixed in place, and they do not remain perfectly separated from each other, because gravity acts over vast distances, slowly pulling massive objects together and shaping their paths through space. And when two galaxies come close enough, even if they do not collide directly in a head-on impact, their gravitational fields begin to interact in ways that can produce large-scale changes in both systems, altering their structures and redistributing their internal material. In the case of Messier 82 and Messier 81, their interaction did not happen as a sudden crash or a dramatic collision in the way that might be imagined, but instead as a close encounter where the gravitational pull of each galaxy began to affect the other, stretching and distorting their shapes, and, most importantly, influencing the movement of gas within them. This type of interaction is driven by what scientists call gravitational tidal forces, which occur when the gravitational pull on one part of an object is stronger than the pull on another part, creating a difference in force that stretches the object and pulls its material in specific directions. And while this concept is often explained using simpler examples like ocean tides on Earth, on the scale of galaxies, the effect is far more powerful and can reshape entire systems over time. As Messier 82 moved through the gravitational field of Messier 81, these tidal forces began to act on its structure, pulling on its outer regions and affecting the distribution of gas within it. And unlike stars, which are relatively stable and follow predictable orbits, gas is much more flexible and responsive to external forces, meaning that it can be moved, compressed, and redirected more easily under the influence of gravity. One of the most important effects of this interaction was the way it pulled gas inward toward the center of Messier 82, because as the gravitational forces acted on the galaxy, they disrupted the normal balance that kept gas spread out across its structure, causing large amounts of material to lose angular momentum and begin moving toward the central regions, where it became more concentrated. This inward movement of gas is a critical step in understanding what happened next, because when gas becomes concentrated in a smaller volume, its density increases. And as density increases, the conditions become more favorable for star formation, since gravity can more easily pull the gas together into collapsing regions that eventually form stars. The process did not happen in a smooth or gentle way, but rather as a complex flow of material being redirected and compressed, with streams of gas being stretched and pulled along the paths defined by the gravitational interaction, creating patterns that can be imagined as long flowing currents of matter moving through the galaxy, colliding with other streams, and building up in certain areas. These gas streams did not move quietly or without resistance, because as they were dragged and compressed, they interacted with each other, creating regions of higher pressure where the material became even denser. And it is in these regions that the conditions for star formation became extreme, with multiple parts of the gas cloud reaching the point of collapse at the same time. Visually, this can be understood as a kind of cosmic distortion, where the galaxy is being stretched and pulled in different directions, while at the same time its internal material is being pushed inward and compressed, creating a network of dense regions connected by streams of gas that are constantly moving and changing under the influence of gravity. The effect of this tidal interaction was not limited to a single area or a small region, but instead affected the galaxy as a whole, because the forces involved were acting on large scales, influencing the distribution of gas throughout the system and setting off a chain reaction that would lead to widespread changes in its behavior. As more gas was pulled into the central regions of Messier 82, the density there continued to rise, and with it, the rate of star formation increased rapidly, moving beyond the steady pace seen in normal galaxies and entering a phase where stars were being formed in large numbers over relatively short periods of time. This increase in star formation did not remain isolated, because the energy released by newly formed stars began to interact with the surrounding gas, further compressing some regions while dispersing others, creating a dynamic environment where the initial effects of the gravitational interaction were amplified by the processes taking place within the galaxy itself. The idea of runaway star formation becomes important here, because once the process begins at a high enough intensity, it can sustain itself through feedback mechanisms, where the energy from one generation of stars contributes to the formation of the next, leading to a cycle that continues as long as there is enough gas available to support it. In Messier 82, the tidal forces from its interaction with Messier 81 provided the initial push that set this process in motion, pulling gas inward and creating the conditions needed for rapid star formation. And once those conditions were established, the galaxy entered a state where its internal processes began to drive further activity, maintaining a high level of star formation across large parts of its structure. The visual image of gas streams being dragged and compressed is not just a simplified way of describing the process, but a reflection of what is actually happening on a physical level as material moves through the galaxy under the influence of gravity, colliding, merging, and building up in dense regions that act as the birthplaces of new stars. These streams can be thought of as pathways along which gas is transported and concentrated, and as they intersect and overlap, they create zones of even higher density where the probability of star formation increases dramatically, leading to clusters of new stars forming in relatively small areas. At the same time, the stretching effect of tidal forces can also pull material outward, creating extended features and distortions in the galaxy's shape. But in the case of Messier 82, the inward movement and compression of gas played the dominant role in triggering its intense star-forming activity. The overall result of this interaction was not a return to stability, but the opposite, as the galaxy entered a state of widespread instability, where the normal balance between gravity, pressure, and motion was disrupted, and the system began to behave in ways that were far more dynamic and unpredictable than before. Galaxy-wide instability means that the effects of the interaction are not confined to one region, but influence the behavior of the entire system, altering how gas moves, how stars form, and how energy is distributed, creating a situation where multiple processes are occurring simultaneously and interacting with each other in complex ways. In this state, the galaxy is no longer operating under the slow, steady conditions that define more typical systems, but is instead undergoing rapid changes driven by both external forces, such as the gravitational pull of Messier 81, and internal processes, such as the energy released by star formation. The interaction between these factors creates a feedback loop where the initial disturbance caused by the tidal forces leads to increased star formation, which in turn produces more energy, which then affects the distribution of gas, potentially leading to further compression and additional star formation, sustaining the cycle over time. This is what makes the trigger so important, because without the initial gravitational interaction, the conditions needed for this level of activity might not have developed, and the galaxy could have remained in a more stable state, forming stars at a slower and more controlled rate. Instead, the close encounter with Messier 81 acted as a catalyst, transforming Messier 82 from a relatively normal system into one experiencing extreme conditions, driven by the redistribution of its internal material and the resulting increase in gas density and star formation. The idea of galaxies interacting in this way is not unique to this single case, as many galaxies in the universe are influenced by their neighbours. But what makes this situation stand out is the scale and intensity of the changes that occurred, leading to a level of activity that is far beyond what is typically observed. As the effects of the tidal interaction continued to shape the galaxy, the instability it created became a defining feature of Messier 82, influencing everything from its structure to its energy output, and setting the stage for the extreme conditions that would later be observed in greater detail. The trigger, therefore, is not just a single event, but a process that unfolds over time, beginning with the gravitational interaction between two galaxies and leading to a cascade of changes that transform one of them into a system defined by rapid star formation and widespread instability. This chain of events, starting with the influence of Messier 81 and continuing through the redistribution and compression of gas, explains how Messier 82 was pushed into its current state, where the balance of forces within the galaxy has been disrupted, and where the processes driving its behaviour operate at a level of intensity that sets it apart from more stable systems. The core, a stellar war zone. At the heart of Messier 82 lies a place that could only be described as a battlefield on a cosmic scale, a region where the normal calm and balance of a galaxy have been entirely replaced by relentless activity, chaos, and energy. Unlike more stable galaxies, where stars are formed at a leisurely pace and their effects on the surrounding environment are relatively mild, the core of Messier 82 is a concentrated hub of destruction and creation occurring simultaneously, a place where the sheer number of massive young stars, combined with the density of the surrounding gas, produces conditions that are nothing short of extreme. One of the first things astronomers notice about this central region is the extraordinary concentration of massive stars. These are not ordinary stars like our Sun, but giants that burn far hotter and release vastly more energy over much shorter lifespans. In a normal galaxy, massive stars are relatively rare and spread out, their formation balanced by the available gas and the limitations of gravitational collapse. In Messier 82, however, these massive stars are packed tightly together in clusters, often forming in groups where their combined influence dramatically alters the surrounding environment. Each star emits immense radiation, primarily in the form of ultraviolet light, which heats the surrounding gas and pushes against nearby clouds, creating a dynamic interplay of forces within the galactic core. Alongside the stars themselves, the core is filled with dense clouds of gas, primarily hydrogen, but also other elements that contribute to the ongoing processes of star formation. These clouds are far more concentrated than in the outer regions of the galaxy, a result of both the tidal forces from Messier 81 and the feedback from previous generations of stars. As the gas is compressed, it becomes highly unstable, collapsing in some areas to form new stars while being heated and pushed outward in others. This constant cycle of compression and expansion creates an environment that is in perpetual motion, with pockets of gas continually shifting under the influence of gravity and the energetic forces from nearby stars. The temperatures in the core reach staggering levels. In some regions, gas heated by intense radiation and shock waves reaches millions of degrees, far beyond the warmth produced in typical galactic environments. These extreme temperatures contribute to the violent behavior observed in the core, as hot gas expands rapidly, collides with other clouds, and drives turbulent motions that ripple through the surrounding material. It is not simply hot. It is a furnace where energy is continuously injected into the system, keeping the core in a state of constant activity. Radiation levels in the core are equally extreme. Ultraviolet light from massive young stars bathe the surrounding gas, ionizing it and altering its chemical state. At the same time, X-rays produced by stellar winds and shock interactions penetrate the dense clouds, further energizing the environment. This combination of radiation types makes the core inhospitable by any normal standard, where the energy released could strip the atmosphere from planets, destroy biological molecules, or even influence the structure of nearby stars. It is a level of intensity that turns the core into a laboratory of extremes, where the rules that apply in quieter parts of the galaxy are stretched to their limits. The core is also a region of constant motion and collision. Shock waves produced by supernova explosions from massive stars race outward, colliding with dense clouds of gas and other shock waves in a continuous overlapping pattern. These interactions compress some regions further while dispersing others, creating pockets of density that become the seeds for new star formation, even as nearby areas are blown apart. Stellar winds from massive stars add another layer of complexity, flowing outward at hundreds or even thousands of kilometers per second, colliding with each other and with gas clouds, and generating turbulence that keeps the environment in a state of perpetual disruption. Everywhere one looks in the core, there is evidence of violent activity. Observations in multiple wavelengths, from radio to infrared to X-ray, reveal filaments of gas being pushed outward, shock fronts expanding through the medium and regions where radiation is so intense that it can alter the chemical composition of the gas itself. Unlike a calm stellar nursery, this core is a battlefield where energy is released, absorbed, redirected and recycled in ways that maintain an ongoing cycle of creation and destruction. The density of stars and gas clouds also means that interactions between stellar systems are more frequent. Collisions of stellar winds from adjacent massive stars are a constant feature, creating localized regions of high pressure and temperature. These collisions are not gentle. They produce shock waves that can travel across vast distances, compressing gas, igniting new rounds of star formation, or in some cases, dispersing material so violently that star formation in that region is temporarily suppressed. This constant push and pull creates a dynamic environment where no part of the core remains static for long. In addition to collisions of stellar winds, the energy from supernova explosions compounds the effects. Massive stars in this region live fast and die young, often within just a few million years, compared to billions of years for smaller stars like the Sun. When these stars explode, they release tremendous energy into the surrounding gas, producing shock waves that expand outward at thousands of kilometers per second. These supernovae do more than just destroy nearby material. They inject energy that drives turbulence across the core, reshaping clouds, compressing regions for new star formation, and sustaining the overall chaotic state. The combination of massive stars, dense gas clouds, extreme temperatures, high radiation levels, shock waves, and colliding stellar winds makes the core of Messier 82 unlike any calm or ordinary galactic center. It is a war zone in every sense of the word. Regions are constantly being shaped and reshaped. Energy is being released and absorbed. And the normal balance between creation and destruction that exists in most galaxies is replaced by a state of ongoing conflict. This environment is also a self-sustaining system in some ways. As stars form and die, they influence the distribution and behavior of the gas, which in turn drives more star formation, creating a feedback loop that perpetuates the intense activity. The density of the core ensures that these interactions happen frequently and continuously, and the concentration of energy prevents the system from settling into equilibrium. Each generation of stars contributes to the turbulence and energy of the next, maintaining the core as a site of perpetual stellar warfare. Even from a distance, this region stands out. Observations of Messier 82 across the electromagnetic spectrum show intense emission from the core, with X-rays and ultraviolet radiation highlighting the most active areas. Filaments of gas ejected by supernovae, arcs created by colliding stellar winds, and dense knots of star-forming regions are all visible in detailed imaging, creating a picture of constant activity and high-energy processes that dominate the center of the galaxy. The core's structure is tightly packed, meaning that the forces at play interact on very small scales relative to the galaxy's size. Massive stars are close enough for their winds to collide directly, for shockwaves to interfere with one another, and for gas clouds to be pushed or compressed by multiple energy sources simultaneously. This density amplifies every effect, ensuring that no part of the core can remain unaffected for long. Temperature extremes are also critical to understanding this war zone. Gas heated to millions of degrees expands rapidly, and when it collides with cooler clouds, it generates turbulence and pressure fronts that propagate through the surrounding medium. These interactions do not occur in isolation. They happen constantly, creating a dynamic environment in which conditions can change dramatically over short distances, even while the overall structure of the core remains relatively confined. Radiation levels are similarly extreme. The combination of ultraviolet and X-ray emission from massive stars and supernovae ensures that the surrounding gas is ionized and energized, influencing both chemistry and dynamics. Molecules that would normally survive in cooler, less energetic regions are broken apart, while atoms are stripped of electrons, altering the behavior of the gas and contributing to the ongoing instability. Shockwaves are not a rare occurrence here. They are constant. Each new massive star adds to the background of pressure waves moving through the medium. Each supernova explosion adds a massive pulse of energy, and collisions between stellar winds create local disturbances that spread outward. These shockwaves compress some regions while dispersing others, contributing to the cycle of creation and destruction that defines the core. The constant collisions of stellar winds further amplify this effect. Massive stars in close proximity produce winds that move at incredible speeds, and where these winds meet, they generate turbulent regions of high temperature and pressure. These interactions are not confined to small areas. They propagate outward, influencing nearby gas clouds, altering star formation patterns, and maintaining the high-energy environment. The result is a central region where the rules of normal galactic life do not apply. The combination of dense star clusters, massive young stars, extreme temperatures, high radiation levels, shock waves, and colliding winds creates a core that is fundamentally unstable, constantly changing, and full of energy. It is a place where stars are born and die at an accelerated rate, where gas is compressed and dispersed in a never-ending cycle, and where the forces driving the galaxy's behavior are concentrated in one intense, chaotic hub. This stellar war zone is visible not only in the energetic signatures astronomers can measure, but also in the structure of the core itself. Filaments of gas, arcs created by shocks, and dense star clusters can be seen in multi-wavelength observations, revealing the complexity and scale of the processes taking place. It is a dynamic, high-energy environment that stands in stark contrast to the more serene outer regions of the galaxy, where star formation occurs at a slower pace and conditions are far less extreme. Every aspect of the core, from its massive stars to its dense gas clouds, from its temperatures to its radiation levels, contributes to a continuous state of upheaval. Shockwaves ripple through the medium, stellar winds collide in unpredictable ways, and regions of gas are constantly compressed and redistributed. The balance between creation and destruction is constantly shifting, and no part of the core remains untouched by the energy that saturates it. The central region of Messier 82, therefore, is not merely a site of rapid star formation. It is a concentrated battlefield where energy, matter, and radiation interact in ways that are extreme, continuous, and self-reinforcing. It is a stellar war zone, a place where the normal calm of a galaxy has been replaced by relentless activity, and where the processes that define life and death for stars are accelerated to an intensity that is almost unimaginable in more stable environments. The supernova overload. At the heart of Messier 82, the extreme star formation in the core inevitably leads to one of the most violent consequences imaginable: a supernova overload. In any galaxy, stars are born, live out their lives, and eventually die. But the conditions inside Messier 82 accelerate this cycle dramatically. Because the core is packed with massive young stars, many dozens or hundreds of times the mass of our Sun, these stars burn through their fuel at incredible rates. While a star like the Sun has a lifespan measured in billions of years, massive stars live fast and die young, often exhausting their nuclear fuel in just a few million years. The short lifespans of these giants mean that Messier 82 experiences a far higher frequency of supernova explosions than any normal galaxy of comparable size. In a typical galaxy such as the Milky Way, supernova occur relatively infrequently, maybe 1 or 2 per century. In Messier 82, however, the combination of extreme star formation and dense clustering of massive stars pushes the supernova rate much higher. Observations suggest that the galaxy may experience multiple supernovae per year, concentrated in the central regions. This creates an environment unlike anything seen in more typical systems, a place where explosions of unimaginable energy are happening continuously, shaping the very structure of the galaxy. Each supernova is not just an isolated event. When a massive star reaches the end of its life, the core collapses under gravity, leading to a titanic explosion that releases as much energy in a few seconds as the Sun will emit over its entire 10 billion year lifespan. This energy is injected into the surrounding gas, heating it to millions of degrees, generating shock waves that travel through the galaxy, and compressing nearby regions of gas that can trigger the formation of new stars. In Messier 82, the sheer number of these events creates overlapping shock waves that collide and interact, generating turbulence on scales that span hundreds or thousands of light years. These repeated explosions constantly reshape the galaxy. Dense gas clouds are compressed in some regions, igniting bursts of star formation, while other areas are blown apart and temporarily cleared of material. The result is a galaxy in constant flux, with the supernovae acting as both creators and destroyers. Their energy drives gas out of the core, feeding the galactic superwind that flows perpendicular to the galaxy's plane, while at the same time generating localized regions where star formation accelerates due to compression of molecular clouds. One of the most famous recent supernovae observed in Messier 82 is SN 2014J. Detected in January 2014, SN 2014J was classified as a Type 1a supernova, meaning it originated from the thermonuclear explosion of a white dwarf in a binary system. Even though Type 1a supernovae are different from the core collapse supernovae produced by massive stars, its occurrence within this galaxy highlights the extreme energy environment of Messier 82. Observations of SN 2014J allowed astronomers to measure the immense energy released during the explosion, which briefly outshone the rest of the galaxy in visible light, and produced vast amounts of high-energy radiation, including X-rays and gamma rays. The energy released by supernovae in Messier 82 is not limited to radiation. Kinetic energy from the explosion propels gas outward at thousands of kilometers per second. This movement injects turbulence into the surrounding medium, constantly disturbing the interstellar gas and contributing to the chaotic environment of the core. These powerful blasts create expanding shock fronts, which interact with gas clouds, other shock waves, and stellar winds from nearby massive stars. The result is a turbulent, dynamic system where the energy released by one star immediately affects its neighbors, ensuring that the cycle of destruction and creation continues without pause. Supernovae also play a critical role in the production and distribution of heavy elements. When a massive star explodes, it synthesizes elements heavier than hydrogen and helium, including oxygen, carbon, iron, and many others, through nucleosynthesis in the core during its life and in the explosion itself. These elements are ejected into the surrounding interstellar medium, enriching the galaxy's gas with materials that will eventually be incorporated into new stars, planets, and potentially the building blocks of life, although Messier 82's extreme conditions make it entirely inhospitable for life as we know it. The enrichment of the interstellar medium with heavy elements is a cumulative process. Each supernova contributes more material, gradually increasing the metallicity of the galaxy. In Messier 82, with its frequent supernova events, this enrichment occurs much faster than in quieter galaxies. Observations in infrared and radio wavelengths have revealed dense clouds of gas rich in heavy elements, evidence of multiple generations of massive stars dying and seeding their environment with the products of their nuclear fusion. In addition to producing heavy elements, the repeated supernovae contribute to the large-scale outflows observed in Messier 82. Known as the galactic superwind, this outflow is a direct result of the combined energy from stellar winds and supernova explosions. Gas is heated, ionized, and expelled from the core at speeds of hundreds of kilometers per second, carrying not just energy, but also newly formed elements out of the galaxy's plane and into intergalactic space. This ongoing process gradually shapes the structure of Messier 82, altering its morphology and influencing the star formation potential in both the core and outer regions. The frequency of supernovae ensures that the galaxy's environment remains in a perpetual state of upheaval. New explosions follow closely after previous ones, meaning that the interstellar medium never has a chance to fully settle. Shockwaves intersect and collide, heating gas, compressing clouds, and producing regions of extreme pressure and temperature. This constant activity maintains the galaxy as one of the most violent star-forming systems in the nearby universe. Supernovae also influence the visibility of Messier 82 across the electromagnetic spectrum. High-energy radiation from these explosions contributes to the galaxy's X-ray and ultraviolet brightness, while the heated gas emits strongly in infrared, helping astronomers trace the structure and activity of the core. Observations of multiple supernova events over time have allowed scientists to map the movement of gas and the evolution of star-forming regions, revealing the ongoing transformation driven by these cataclysmic explosions. SN 2014J, in particular, provided a wealth of information. Its proximity, at just about 12 million light-years away, made it one of the closest Type 1a supernovae observed in recent decades, allowing astronomers to measure the explosion in unprecedented detail. They could observe the light curve, the spectrum of elements produced, and the interaction of the ejected material with surrounding gas. The data confirm not only the immense energy released, but also the way such an explosion contributes to the dynamic processes shaping Messier 82, from feedback into star formation to enrichment of the interstellar medium. In Messier 82, the cumulative effect of frequent supernovae is far more dramatic than in normal galaxies. Each explosion propagates energy and material through the galaxy, interacting with neighbouring stars, gas clouds, and prior supernova remnants. These overlapping effects amplify the violence of the core, turning the central region into a sustained zone of chaos and transformation. The galaxy's appearance, its radiation output, and the distribution of gas and elements are all profoundly influenced by this overload of stellar deaths. This environment also changes the life cycle of subsequent stars. Massive stars forming in the core are born into regions already energized by previous supernovae, affecting how their own formation progresses. Shockwaves compress clouds in some regions while dispersing gas in others, determining where the next generation of stars will emerge. This creates a complex self-reinforcing cycle. Star formation leads to supernova. Supernova energize and compress gas, and the compressed gas fuels further star formation, maintaining Messier 82's extraordinary activity over millions of years. In short, the supernova overload in Messier 82 is a defining feature of the galaxy. Massive stars with short lifespans produce explosions at a rate far higher than seen in normal galaxies. These repeated explosions reshape the structure, dynamics, and chemical composition of the galaxy, while individual events like SN 2014J highlight the enormous energy released and the production of heavy elements that enrich the interstellar medium. The combined effect of these processes ensures that Messier 82 remains a constantly evolving, extreme, and violent environment, where the normal order of stellar life and death is pushed to its limits. The core of the galaxy, already a war zone of stellar winds and colliding shock waves, is further dominated by this near-continuous barrage of supernova explosions. Each blast contributes to the turbulence, energizes the surrounding gas, and drives outflows into the wider galaxy. Collectively, these events define Messier 82 as one of the most extraordinary and destructive star-forming systems in the nearby universe, illustrating how the life cycle of massive stars, when accelerated and concentrated, can transform an entire galaxy into a landscape of relentless energy and constant upheaval. Galactic superwind, the signature horror. At the core of Messier 82, the extreme star formation and constant supernova explosions give rise to one of the most spectacular and terrifying phenomena in the nearby universe, the galactic superwind. This is not a gentle breeze of gas drifting through space. It is a massive, high-speed outflow driven by the combined energy of countless stellar deaths and powerful stellar winds from massive young stars. In Messier 82, these superwinds reach speeds exceeding 1,000 kilometers per second, fast enough to sweep entire clouds of gas and dust out of the galaxy's core and into intergalactic space. The structure of this superwind is distinctive. Rather than dispersing evenly in all directions, the outflows form a bipolar pattern, shooting outward above and below the galaxy's plane. From the side, Messier 82 appears as a flattened disk, but from this perspective, twin plumes of gas and energetic particles extend perpendicular to the disk, forming towering columns that span tens of thousands of light years. These columns are the visible signature of the galactic superwind, and they define much of what astronomers refer to when calling Messier 82 the most horrific galaxy. The composition of these outflows is as violent as their speed suggests. The gas is highly ionized due to the extreme radiation from the core and the repeated supernova explosions. It is mixed with dust particles and metals produced in the explosions of massive stars, including elements such as oxygen, carbon, iron, and heavier atoms formed through nucleosynthesis. This combination of hot, energized gas and enriched material is being expelled at a pace that continually reshapes the galaxy's structure. It is a force that not only sculpts the interstellar medium within Messier 82, but also enriches the surrounding intergalactic environment with newly formed elements. Superwinds like these do not form slowly. They are the direct consequence of the repeated injection of energy from supernova and stellar winds over millions of years. Each supernova produces a blast wave that pushes against the surrounding gas, creating pockets of pressure. When many of these explosions occur in rapid succession, the overlapping shock waves amplify the effect, accelerating the gas outward at incredible velocities. The bipolar structure arises naturally because the densest gas in the galactic plane resists movement, forcing the outflow along the path of least resistance, above and below the disk. These superwinds are not just a visual phenomenon. They are powerful enough to impact the dynamics of the entire galaxy. Gas expelled from the core reduces the material available for new star formation, altering the balance of the galaxy over time. However, this process is not uniform. Some dense gas clouds remain trapped within the gravitational pull of the galaxy and continue forming stars, while the less dense material is accelerated outward. This selective removal of gas contributes to the uneven and violent appearance of Messier 82, reinforcing the impression of chaos and destruction. The galactic superwind also produces an extraordinary radiation environment. X-ray emissions from the hot gas were detected by the Kundra X-ray Observatory, revealing the high temperatures and energetic processes at work. In addition to X-rays, gamma rays and cosmic rays flood the galaxy, carrying enormous amounts of energy far from their points of origin. These high-energy particles penetrate the interstellar medium, ionizing gas and breaking molecular bonds, and in some cases altering the chemistry of the galaxy on large scales. The impact of this radiation on matter is profound. Molecular clouds, which are the birthplaces of stars, are bombarded with ionizing radiation, disrupting the delicate balance of molecules needed for star formation. Dust grains can be heated, eroded, or even destroyed, while cosmic rays create further ionization and chemical changes. In essence, the galactic superwind not only moves material physically, but also transforms it chemically, creating a highly energized, unstable environment where traditional rules of molecular chemistry are constantly challenged. The combination of the superwind and the radiation environment is what gives Messier 82 its horrific reputation among astronomers. It is not merely that stars are forming at high rates or that supernovae are frequent. It is that the energy output from these processes drives a continuous, galaxy-wide disturbance. Hot gas, dust, metals, X-rays, gamma rays, and cosmic rays all interact in a complex network of forces, reshaping the core and driving matter outward at velocities that dwarf anything found in calmer galaxies. Observationally, the superwind is visible across multiple wavelengths. Optical images show glowing filaments of gas extending above and below the disk. Infrared data highlight the heated dust and embedded star-forming regions, and X-ray observations reveal the searing hot plasma streaming outward. Each wavelength provides a different perspective on the same violent processes, together painting a picture of a galaxy in constant upheaval. The energy carried by the superwind is immense. The combined power of overlapping supernovae and stellar winds creates a feedback loop. Energy accelerates gas. Gas collides with other material. Collisions produce shocks, and shocks release further energy, which then drives more outflows. This cycle sustains the bipolar superwind and maintains the extreme environment of Messier 82 over millions of years. In addition to shaping the galaxy itself, these outflows have far-reaching consequences. As material is expelled into intergalactic space, it contributes to the enrichment of the surrounding medium with metals and ionized gas. In this way, the superwind acts as both a destructive and creative force, It strips the core of gas that could form stars while simultaneously dispersing elements that will seed future star formation elsewhere in the universe. Cosmic rays generated in the core propagate throughout the galaxy, interacting with magnetic fields and dense gas clouds. These high-energy particles add another layer of complexity to the superwind's effects, producing ionization and heating on large scales, further enhancing the disruptive conditions within Messier 82. The interplay of mechanical energy from the wind, radiative energy from supernovae, and energetic particles creates a multifaceted environment of unparalleled intensity. The bipolar structure is particularly striking. Gas and plasma are funneled out above and below the galactic plane, forming twin plumes that extend tens of thousands of light years from the core. Within these plumes, filaments of hot ionized gas are threaded with metals and dust, continuously reshaped by shocks and collisions. Observations in X-ray and ultraviolet light reveal that these outflows are not uniform sheets, but dynamic, twisted structures, reflecting the turbulent forces driving them. Hot ionized gas, dust, and metals in the superwind are all subject to continuous motion and interaction. Gas clouds are compressed in some regions and fragmented in others. Metals produced in supernovae are carried along, enriching both the outflow and the surrounding interstellar medium. Dust is heated and sometimes destroyed, contributing to the complex chemistry observed in the plumes. This combination of factors ensures that the galactic superwind is not a static phenomenon, but a constantly evolving, energetic force shaping the galaxy's appearance and behavior. The impact of the superwind on the galaxy's core is equally dramatic. By removing gas from the central regions, the wind regulates star formation, preventing the core from becoming even denser than it already is. However, it does not eliminate star formation entirely. Dense clumps of gas remain gravitationally bound, and these regions continue to collapse under their own weight, forming new generations of massive stars. The ongoing cycle of star formation, supernova explosions, and outflow generation creates a self-sustaining system that maintains Messier 82's extreme character. X-ray emissions detected by Chandra reveal the highest energy regions of the superwind. These emissions trace the hot plasma heated by repeated supernovae and colliding stellar winds. Gamma rays and cosmic rays, also detected in this galaxy, carry additional energy, influencing regions far from the core and interacting with magnetic fields throughout the galaxy. Together, these energetic phenomena produce an environment where traditional notions of calm galactic life are impossible. The galaxy is alive with motion, energy, and constant transformation. The galactic superwind, combined with the radiation environment, explains why Messier 82 is often described as horrific. It is not merely the presence of violent stars or frequent supernovae, but the combination of high-speed outflows, extreme temperatures, ionized gas, metals, dust, X-rays, gamma rays, and cosmic rays interacting simultaneously across the galaxy. Each factor amplifies the others, producing a level of chaos and energy that is rare in the nearby universe. Every element of this process, gas ejection, shock waves, radiation, cosmic rays, and chemical enrichment, contributes to a sustained, self-reinforcing cycle of destruction and transformation. The bipolar superwind carries the signature of the galaxy's extreme activity, visible across multiple wavelengths and serving as a constant reminder that Messier 82 is not a quiet or ordinary system. What happens to planets there? Imagine a planet orbiting a star inside the core of Messier 82. Even before considering life, the very existence of such a planet would be under constant threat from forces far beyond anything experienced in our solar system. The environment is shaped by extreme star formation, frequent supernova explosions, high-speed stellar winds, and a galactic superwind. These factors create conditions that are relentlessly hostile to planetary systems, making the idea of a stable, habitable world almost impossible. The radiation environment alone would be catastrophic. Planets in this region would be bombarded constantly by X-rays, gamma rays, and cosmic rays generated by the dense core's massive stars and supernovae. Unlike the relatively stable radiation levels in our solar system, where the Sun's output is moderate and predictable, planets in Messier 82 would experience fluctuating bursts of energy capable of ionizing gas and stripping electrons from molecules in their atmospheres. Over time, this would erode protective layers such as ozone, allowing even more energetic radiation to penetrate the surface. For any hypothetical atmosphere, this constant bombardment would mean gradual depletion of gases, particularly lighter elements like hydrogen, making long-term atmospheric stability impossible. Even if a planet had a dense atmosphere to start with, the extreme ultraviolet and X-ray flux would strip it away in mere thousands of years, far shorter than the time needed for life to develop. The combination of stellar radiation, supernova shockwaves, and the pressure from the galactic superwind would tear the atmosphere apart, layer by layer. Surface pressure would fluctuate, protective shielding would fail, and the environment would become sterile in a geological instant. Unlike Earth, where an atmosphere is maintained over billions of years, these hypothetical planets would see their gaseous envelopes disappear as quickly as they formed. Surface conditions would be equally catastrophic. The intense radiation would sterilize any exposed organic material, destroying DNA and other molecular structures essential for life. Cosmic rays and high-energy photons would break chemical bonds, leaving the planetary surface lifeless. Even the most basic forms of microbial life could not survive long-term exposure. Liquid water, which is crucial for life as we know it, would be constantly evaporated or dissociated into hydrogen and oxygen by the energetic radiation. Any planetary oceans would not be stable, and the surface would be baked, irradiated, and chemically altered continuously. No stable habitable zones could exist, even if a star had a Goldilocks zone distance where temperatures were moderate enough for liquid water. The surrounding radiation environment would render it irrelevant. Stellar flares, shock waves from nearby supernovae, and the pervasive galactic superwind would flood the system with energetic particles, ensuring that the region could not maintain the calm conditions required for life. Any hypothetical orbiting planets would face fluctuating energy input, intense particle bombardment, and rapid atmospheric loss, making the concept of habitability meaningless in the context of Messier 82. Gravitational interactions add another layer of instability. With so many massive stars packed into the core, planetary orbits would be disrupted frequently. Stars passing nearby would exert tidal forces strong enough to perturb planetary trajectories, potentially ejecting planets from their systems entirely or sending them crashing into their host stars. Combined with the constant bombardment of radiation and supernova material, these dynamic disturbances make any long-term stable planetary system virtually impossible. Even more remote outer regions of the galaxy are not safe. The galactic superwind carries energized gas and particles far from the core, exposing outer planetary systems to high-speed flows of hot, ionized material. While the intensity is lower than in the central regions, the cumulative effect over time would still be enough to strip atmospheres, destroy molecular structures, and prevent any stable climate from forming. Essentially, no part of Messier 82 offers a sanctuary for planets. The entire galaxy is dominated by energetic processes that leave planetary systems in constant jeopardy. This extreme environment also prevents planet formation in many cases. Dense clouds of gas and dust are needed to collapse into protoplanetary disks, Yet the constant shock waves and supernova-driven turbulence disrupt these clouds before they can settle into stable structures. Even if planets did form, their survival would be fleeting. Collisions with high-speed particles, nearby ejecta from exploding stars, and tidal disruptions from gravitational interactions would ensure that most would be destroyed or ejected within a few million years. A mere blink in cosmic terms. The dust problem, why it looks calm. From Earth, Messier 82 appears deceptively calm. Optical images show a bright, elongated galaxy with defined edges, giving the impression of a serene, cigar-shaped nebula floating in the void. Yet this calm appearance is entirely misleading, a visual illusion caused by thick dust clouds that obscure the most violent activity within. These clouds, composed of dense molecular gas, dust, and metals ejected from supernovae, absorb visible light and scatter it, preventing astronomers using traditional optical telescopes from seeing the chaos hidden in the core. What looks like a smooth, steady glow is actually a wall hiding countless violent processes. Infrared observations have been crucial in revealing the hidden turmoil. The Spitzer Space Telescope and other instruments detect heat emitted by dust warmed by the energetic processes in the core, penetrating the obscuring layers to reveal the full intensity of Messier 82's activity. In infrared light, astronomers can see the massive star clusters, the compressed gas clouds, and the hot filaments being accelerated by supernova-driven shocks and stellar winds. These observations provide a window into the chaos that optical telescopes cannot reveal. The contrast between calm appearance and violent reality is stark. In visible light, Messier 82 may seem like a simple, elongated galaxy, perhaps even a peaceful one. But in infrared, the scene changes dramatically. Plumes of hot gas, energetic outflows, and dense clusters of massive stars dominate the view. The core, previously hidden behind thick dust, is revealed as a maelstrom of energy, with violent star formation, supernova explosions, and the onset of the galactic superwind clearly visible. Dust is not just a visual barrier, it also plays an active role in the galaxy's energetic processes. Dust grains absorb ultraviolet and optical radiation, re-emitting it in the infrared. This means that the very dust that obscures the view is heated to high temperatures, becoming an indicator of hidden energy. Infrared imaging therefore serves as a direct map of the galaxy's violent core, showing where energy is being absorbed and redistributed, and where hidden star formation continues at extreme rates. Without infrared observations, Messier 82's true nature would remain largely concealed. Optical telescopes capture only the surface glow, missing the ongoing supernova explosions, shock waves, and high-energy radiation that define the core. The apparent calm is simply the result of dust acting as a filter, hiding the most destructive processes and giving the illusion of serenity. This is why astronomers rely on infrared data to understand not just Messier 82, but many other starburst galaxies, where dust masks the underlying violence. The dust problem also explains why Messier 82 was originally underestimated. Early astronomers observing with optical telescopes saw only a faint nebula, failing to detect the extraordinary starburst activity taking place behind the thick layers of obscuring material. It was only when radio, infrared, and later X-ray observations became available that the galaxy's true nature was revealed. The optical calm belied the extreme energy release, the supernova overload, and the high-speed galactic outflows occurring simultaneously in the core. Infrared observations also provide insights into the structure and composition of the dust itself. Heated by massive stars and supernova energy, the dust emits radiation that allows astronomers to estimate temperatures, densities, and even chemical composition. By mapping the dust, scientists can trace regions of star formation, track the propagation of shockwaves, and identify zones where the galactic superwind is emerging. This multi-wavelength approach reveals that the calm optical exterior hides a galaxy in constant violent motion. The dust problem demonstrates how appearances can be deceiving in astronomy. Messier 82 seems calm in visible light, but the reality is one of extreme energy, turbulence, and destruction. The thick clouds obscure not only light, but also the understanding of the galaxy's processes, until instruments sensitive to infrared, radio, and X-rays reveal the hidden chaos. What appears serene is in fact a theatre of cosmic violence, where stars are born and die rapidly, supernovae explode repeatedly, and matter is continuously energized, expelled, and transformed. Magnetic fields and cosmic chaos. Within the core of Messier 82, the extreme star formation, supernova explosions, and galactic superwind interact with another less visible but equally important force: magnetic fields. These magnetic fields thread through the galaxy, influencing the motion of charged particles, guiding gas flows, and shaping the structure of the galaxy on scales spanning thousands of light years. While invisible to optical observation, their effects are fundamental in organizing and containing the chaos that otherwise might be even more unruly. The magnetic fields in Messier 82 are unusually strong compared to those in normal galaxies. Measurements using polarized radio emissions reveal that the core and outflow regions are threaded with magnetic lines that stretch along the bipolar superwind plumes. These fields act as channels for the hot, ionized gas expelled from the central regions, constraining the motion of particles and partially guiding the flow of matter. Without these fields, the gas would disperse more randomly, and the superwind would likely be less collimated, reducing the dramatic bipolar structure that astronomers observe. Charged particles, including electrons, protons, and heavier ions, accelerated by supernovae and stellar winds, respond strongly to the galaxy's magnetic fields. As these particles spiral along magnetic field lines, they generate synchrotron radiation, which can be detected in radio wavelengths. This emission reveals both the strength and orientation of the fields, showing that they are not random but aligned along the outflow plumes. The magnetic fields therefore serve a dual role. They contain the charged particles, preventing them from dispersing too quickly, and they guide their motion along defined channels, contributing to the observed structure of the galactic superwind. Cosmic rays, high-energy particles traveling near the speed of light, are particularly influenced by these magnetic fields. The particles produced by supernovae and other energetic events in the core are trapped, deflected, and guided along field lines spreading through the galaxy in a complex, structured way. As they travel, they collide with gas clouds, ionizing the material and heating it, further energizing the already extreme environment. The magnetic fields create a framework that contains these particles long enough for them to influence large regions of the galaxy, rather than escaping immediately into intergalactic space. The interaction of magnetic fields with gas and dust also affects turbulence in the galaxy. The magnetic fields therefore play a critical role in structuring the galaxy's violent processes, channeling energy, and enhancing the visual and energetic impact of the superwind. Magnetic reconnection events, where field lines snap and reconnect, can release sudden bursts of energy in localized regions. In Messier 82, these events likely occur frequently due to the turbulence of the core, contributing to additional heating, acceleration of charged particles, and localized bursts of high-energy radiation. These events, though small compared to supernova explosions, add another layer of complexity and chaos to the galaxy, creating pockets of intensified energy and contributing to the constant transformation of gas and dust. The interaction of magnetic fields with the galactic superwind, cosmic rays, and turbulent gas creates a multi-layered environment in which energy is continuously redistributed. Fields guide the motion of charged particles, confine energetic gas, and maintain the structure of outflows, while the constant feedback from supernovae, stellar winds, and turbulence twists and modifies the fields themselves. This dynamic interplay ensures that Messier 82 remains in a state of persistent activity, with magnetic fields both containing and directing the extreme forces unleashed by its starburst core. Magnetic fields also influence the transport of metals and dust. As supernova ejecta and stellar winds expel material into the bipolar plumes, the fields help channel this matter, allowing heavy elements to be carried far from the core without dispersing randomly. This guidance enhances the efficiency of enrichment of the surrounding interstellar and intergalactic medium, concentrating metals and dust along the paths defined by the magnetic fields. In this way, the fields contribute to the galaxy's chemical evolution even while participating in the chaotic dynamics of star formation and feedback. The black hole activity. While the magnetic fields guide charged particles and structure the galaxy, another feature often associated with galactic violence is less significant in Messier 82: black hole activity. Many galaxies, including the Milky Way, have supermassive black holes at their centers, and these black holes can dominate a galaxy's energetic output through accretion of gas and emission of jets. Messier 82, however, tells a different story. The central region of Messier 82 may host an intermediate mass black hole, smaller than the supermassive black holes seen in active galactic nuclei. Observations suggest that this black hole is present but does not dominate the galaxy's energy output. Unlike galaxies where the central black hole drives energetic jets, outflows, and high-energy radiation, Messier 82's extreme behavior comes primarily from starburst activity. The supernova overload, galactic superwind, and massive star formation in the core are the true sources of its violence. This distinction is important. In galaxies dominated by central black holes, such as Sagittarius A star in the Milky Way, the outflows, high-energy radiation, and cosmic particle acceleration originate largely from the black hole's accretion disk and relativistic jets. In Messier 82, the high-energy phenomena, the X-rays, gamma rays, cosmic rays, and hot gas outflows, are instead a product of thousands of massive stars forming and dying in close proximity. Starburst activity, not black hole activity, drives the superwind, structures the magnetic fields, and generates the extreme radiation environment. The lack of a dominant black hole explains why the galaxy's violence is concentrated differently. In black hole-driven systems, energetic jets often focus along narrow axes extending from the core, sometimes far beyond the host galaxy. In Messier 82, the violence is more distributed across the starburst core, with energy injected from multiple supernovae and stellar winds over a broader area. The bipolar superwind emerges from this distributed energy, guided by magnetic fields and shaped by the dense concentration of massive stars rather than a single central engine. The presence of an intermediate black hole may still influence local dynamics slightly. Its gravity can contribute to the overall motion of stars and gas near the very center of the galaxy. However, compared to the overwhelming effects of starburst activity, this influence is minor. The core's chaos, turbulence, and extreme energy levels arise from the cumulative impact of stellar processes rather than accretion onto the black hole. This starburst-driven nature is part of what makes Messier 82 particularly unusual. Many galaxies that exhibit extreme outflows and high-energy emissions are active galactic nuclei, powered by central black holes. Messier 82 demonstrates that similar or even more extreme conditions can be achieved through concentrated star formation alone. The energy released by thousands of massive stars interacting with magnetic fields and producing repeated supernova explosions is enough to create high-speed bipolar outflows, intense radiation fields, and cosmic ray flooding without requiring a dominant black hole. In effect, Messier 82 is a laboratory for studying the impact of starburst activity independent of black hole influence. Astronomers can observe how concentrated star formation alone generates superwinds, structures magnetic fields, accelerates cosmic rays, and produces extreme radiation levels. Instead, the galaxy's extreme behavior arises from the concentrated birth and death of massive stars, making it an exceptional example of how starburst-driven processes can create galactic-scale destruction and energy outflows. This starburst-driven chaos is visible across multiple wavelengths. X-rays, gamma rays, infrared emission from heated dust, and radio emission tracing synchrotron radiation all reveal the effects of massive stars rather than a dominant black hole. Observational data show that the superwind, cosmic ray propagation, and energetic radiation are centered on regions of intense star formation, further confirming that the core's extreme activity originates from starburst processes. The comparison with black hole-dominated galaxies highlights the uniqueness of Messier 82. While both types of galaxies can produce high-energy outflows and radiation, the mechanisms differ fundamentally. In Messier 82, the violence is widespread, distributed across the core, and tightly linked to the life cycle of massive stars. In black hole-driven systems, energy release is more centralized, focused along jets, and regulated by the accretion process. Messier 82 demonstrates that a galaxy does not need a dominant black hole to become one of the most violent, chaotic systems in the nearby universe. By studying Messier 82, astronomers gain insight into the extreme end of starburst activity. The interplay of magnetic fields, supernovae, cosmic rays, and stellar winds illustrates how massive star clusters alone can generate galaxy-wide turbulence, high-energy outflows, and dramatic radiation environments. The intermediate black hole may be present, but it is a minor player, emphasizing that the galaxy's signature horror is entirely starburst-driven. The combination of strong magnetic fields and the distributed starburst-driven energy release makes Messier 82 a unique laboratory. Magnetic fields guide outflows and charge particles, while the repeated deaths of massive stars inject energy and material into the interstellar medium. The intermediate black hole may influence local dynamics slightly, but it does not control the large-scale structure or radiation environment. This separation of mechanisms allows astronomers to isolate the effects of starburst activity and study how concentrated massive star formation alone can create extreme conditions typically associated with black hole activity. Comparison with normal galaxies. To understand just how extreme Messier 82 really is, it helps to place it side by side with what astronomers call normal or stable galaxies. These stable galaxies make up the majority of systems in the universe. They follow a more balanced, steady pattern of star formation, gas usage, and energy output. Nothing in them happens too quickly, and nothing spirals out of control. In contrast, Messier 82 behaves in a way that breaks this balance completely, pushing every process to an extreme level. In a stable galaxy, star formation is regulated. Gas clouds collapse slowly under gravity, forming stars at a pace that can be sustained for billions of years. The amount of gas available is large, but it is used carefully, almost like a controlled resource. New stars are created, but not in overwhelming numbers, and certainly not all at once. This creates a steady rhythm. Stars form, live their long lives, and eventually die, returning material back into the galaxy to be reused in future generations. The cycle is smooth and continuous. Take a galaxy like the Milky Way. It produces only about 1 or 2 new stars each year. this may sound like a lot, but on a galactic scale, it is actually very modest. The Milky Way has enough gas to continue forming stars at this rate for billions of years. Its star formation is spread out across the disk, not concentrated in one violent core. This distribution prevents any single region from becoming too unstable or energetic. The galaxy remains calm, with localized activity, but no overall chaos. Messier 82 is the opposite of this balance. Instead of slow and steady star formation, it experiences an intense burst of activity. Gas is not used gradually. It is consumed rapidly, almost all at once. The central regions are packed with dense clouds collapsing simultaneously, producing massive numbers of stars in a short period. This is what defines a starburst galaxy, but in Messier 82, the effect is pushed to an extreme level. The rapid consumption of gas is one of the most important differences. In stable galaxies, gas reservoirs last for billions of years because the rate of star formation is low. In Messier 82, the gas is being used up far faster than it can be replaced or redistributed. Every new generation of stars consumes large amounts of material, and the repeated supernova explosions and galactic superwind also push gas out of the galaxy entirely. This means that the total supply of star-forming material is shrinking quickly. This rapid depletion creates a sense of urgency in the galaxy's behavior. It is as if all the fuel is being burned at once, rather than saved for a long, steady process. The result is a period of extreme brightness, high energy output, and intense activity. But it cannot last forever. The galaxy is effectively using up its resources in a short burst, rather than spreading them out over cosmic time. In stable galaxies, feedback mechanisms help maintain balance. When stars form, they produce radiation and stellar winds that can slow down further star formation by heating and dispersing gas. Supernovae also play a role, injecting energy into the surrounding medium. However, because these events are relatively rare and spread out, they do not overwhelm the system. Instead, they act as regulators, preventing runaway star formation. In Messier 82, these feedback mechanisms are still present, but they operate on a completely different scale. The sheer number of massive stars and supernovae means that the energy being injected into the galaxy is enormous. Instead of gently regulating star formation, this energy drives powerful outflows and turbulence. Gas is compressed in some regions, triggering even more star formation, while in others it is blown away entirely. The system becomes unstable, with no steady equilibrium. Another key difference lies in how energy is distributed. In stable galaxies, energy from star formation and stellar death is spread out over large areas. This prevents any one region from becoming too extreme. In Messier 82, energy is concentrated in the core, where star formation is most intense. This concentration amplifies every effect: radiation, shock waves, and gas motion, creating a feedback loop that sustains the galaxy's violent behavior. The structure of the galaxy also reflects this difference. Stable galaxies often have well-defined shapes, such as spiral arms or smooth elliptical forms. These structures remain relatively consistent over long periods of time. In Messier 82, the structure is more chaotic. The core is highly active, and the presence of the galactic superwind creates large-scale outflows that extend far beyond the disk. The overall appearance is more disturbed, reflecting the intense processes occurring within. Time is another crucial factor. Stable galaxies evolve slowly. Their star formation rates change gradually, and their overall structure remains intact for billions of years. Messier 82, however, is undergoing a phase that is relatively short in cosmic terms. The starburst phase, where star formation is extremely high, does not last indefinitely. Because the galaxy is consuming its gas so quickly, this phase is expected to end much sooner than the lifespan of a typical galaxy. This difference in timescale highlights the temporary nature of Messier 82's current state. While it appears extremely active and energetic now, this level of activity cannot be sustained over billions of years. Once the gas supply is depleted or reduced significantly, the rate of star formation will drop. The galaxy will eventually transition into a more stable state, but not before undergoing a dramatic period of transformation. In stable galaxies, the long lifespan of star formation allows for multiple generations of stars to form in a balanced way. Older stars coexist with younger ones, and the galaxy maintains a mix of different stellar populations. In Messier 82, the rapid burst of star formation means that many stars are formed at nearly the same time. This creates large populations of young, massive stars that dominate the galaxy's energy output. Over time, as these stars die, the balance will shift again, but the current phase is heavily weighted toward youth and intensity. Gas dynamics also differ significantly. In stable galaxies, gas moves relatively slowly, influenced by gravity and moderate stellar feedback. In Messier 82, gas is constantly being pushed, compressed, and expelled by powerful forces. The galactic superwind carries material away at high speeds, while shock waves from supernovae create turbulence throughout the core. This constant motion prevents the gas from settling into a stable configuration, further enhancing the chaotic nature of the galaxy. Another contrast lies in the efficiency of star formation. In stable galaxies, only a small fraction of gas is converted into stars at any given time. Much of the gas remains in clouds, available for future star formation. In Messier 82, the efficiency is much higher. Large amounts of gas are rapidly converted into stars, leaving less material for the future. This high efficiency contributes to the short lifespan of the starburst phase. The visual appearance of the galaxy also reflects these differences. Stable galaxies often appear calm and orderly, with smooth light distribution and predictable structures. Messier 82, even when partially obscured by dust, shows signs of disturbance. Infrared and X-ray observations reveal intense activity, outflows, and energetic processes that are not present in more balanced systems. The galaxy's brightness, especially in high-energy wavelengths, is a direct result of its extreme star formation and rapid gas consumption. The environment around the galaxy is also affected differently. Stable galaxies have relatively mild interactions with their surroundings, gradually exchanging gas and energy over long periods. Messier 82, through its superwind, actively expels material into intergalactic space. This outflow carries gas, dust, and heavy elements far from the galaxy, influencing the surrounding medium in a more immediate and dramatic way. Even the life cycle of stars within the galaxy reflects the contrast. In stable galaxies, stars form at a range of masses, with many small, long-lived stars and fewer massive, short-lived ones. In Messier 82, the intense conditions favor the formation of massive stars. These stars dominate the energy output, but have very short lifespans, leading to frequent supernova explosions. This cycle reinforces the galaxy's extreme behavior and distinguishes it from more balanced systems. The concept of balance is central to understanding the difference. Stable galaxies maintain an equilibrium between star formation, gas consumption, and energy output. Messier 82 operates far from equilibrium. Every process is amplified, accelerated, and interconnected in a way that prevents stability. Gas is consumed rapidly, energy is released in large amounts, and feedback processes drive further activity rather than regulating it. The relatively short lifespan of the starburst phase is a direct consequence of this imbalance. Because the galaxy is using its resources so quickly, it cannot sustain the same level of activity for long. In cosmic terms, this phase may last only tens of millions of years, compared to the billions of years over which stable galaxies evolve. This makes Messier 82 a snapshot of an extreme but temporary stage in galactic evolution. During this short period, the galaxy undergoes rapid changes. Star formation peaks, supernova rates increase, and the galactic superwind becomes more pronounced. As gas is depleted and expelled, the conditions that drive the starburst begin to weaken. Over time, the galaxy will move toward a more stable state, but the current phase leaves a lasting impact on its structure, composition, and surrounding environment. The comparison with normal galaxies highlights just how unusual Messier 82 is. While most galaxies follow a steady, long-term pattern, Messier 82 compresses intense activity into a short period. It burns through its gas quickly, produces stars at a high rate, and releases enormous amounts of energy. This makes it one of the most extreme examples of starburst activity in the nearby universe. The contrast is not just in scale, but in behavior. Stable galaxies are predictable, with gradual changes and long-term stability. Messier 82 is dynamic, with rapid changes and short-term intensity. The difference between the two represents different modes of galactic evolution. One slow and sustained, the other fast and explosive. The long-term fate. The long-term fate of a galaxy like Messier 82 is shaped almost entirely by one central process, the loss and exhaustion of its gas. Gas is the raw material needed to form new stars. Without it, the entire system begins to change. Every bright, violent, and energetic feature seen during its active phase is tied to how much gas is available and how quickly it is being used. Once that supply begins to run low, the character of the galaxy shifts in a slow but unavoidable way. At the heart of this transformation is gas depletion. In its current state, the galaxy is consuming gas at a very high rate. Dense clouds collapse quickly, forming stars in large numbers. At the same time, powerful outflows push gas away from the central regions and even out of the galaxy entirely. These two processes, rapid consumption and active removal, work together to reduce the total amount of gas available. Gas depletion does not happen all at once. It is a gradual process, but in a system like this, it happens much faster than in more stable galaxies. Each new generation of stars requires large amounts of gas. Massive stars, which are common in this environment, consume more material and live shorter lives. When they explode as supernovae, they do not return all their material in a calm way. Instead, they inject energy into the surrounding space, heating the gas and pushing it outward. Some of that gas becomes too hot or too dispersed to collapse again into new stars. As time passes, the dense gas clouds that once filled the central regions begin to thin out. The number of regions where star formation can occur starts to drop. The conditions that once allowed stars to form quickly and easily become harder to maintain. The galaxy does not suddenly stop forming stars, but the rate begins to decline. This slowing of star formation is one of the most important steps in the galaxy's long-term evolution. At first, the change may not be obvious. There are still many young stars shining brightly, and some regions continue to produce new ones. But beneath the surface, the overall trend is clear. Fewer new stars are being created over time. The decline in star formation changes the energy balance of the galaxy. During the active phase, massive stars dominate the energy output. They produce intense radiation, strong stellar winds, and frequent supernova explosions. These processes keep the galaxy in a highly energetic and unstable state. As star formation slows, fewer massive stars are born. Over time, the number of these short-lived, high-energy stars decreases. With fewer massive stars, the amount of energy being injected into the galaxy drops. There are fewer supernova explosions, less intense radiation, and weaker stellar winds. The forces that once drove turbulence and outflows begin to weaken. Gas that remains in the galaxy is less disturbed and can begin to settle into more stable patterns. This shift marks the beginning of stabilization. The galaxy moves away from its chaotic, high-energy state and toward a more balanced condition. Stabilization does not mean that all activity stops. Stars still exist, and some star formation continues. However, the extreme conditions that defined the earlier phase are no longer present. As the galaxy stabilizes, its structure becomes more regular. Gas and stars are no longer being pushed around as violently. The central regions, once filled with intense activity, begin to calm down. The large-scale outflows that once extended far beyond the galaxy weaken and may eventually fade away. Without the constant input of energy from massive stars and supernovae, there is no longer enough force to sustain these features. The remaining gas within the galaxy becomes more evenly distributed. Instead of being compressed into dense, rapidly collapsing regions, it spreads out and moves more slowly. This reduces the efficiency of star formation even further. New stars can still form, but the process becomes less frequent and less intense. As time continues, the galaxy enters a quieter state. This is not a sudden change, but a gradual transition. The brightness of the galaxy begins to decrease, especially in wavelengths associated with high-energy processes. The intense glow from hot young stars fades as those stars reach the end of their short lifespans and are not replaced at the same rate. Older stars begin to dominate the light of the galaxy. These stars are cooler and less luminous than massive young stars. They shine steadily, but do not produce the same level of energy or dramatic effects. The overall appearance of the galaxy becomes softer and less extreme. The quieter state also affects the environment within the galaxy. With fewer high-energy events, the interstellar medium becomes less turbulent. Gas and dust can exist in more stable forms. The constant shocks and heating that once disrupted molecular structures become less common. This allows for a more settled internal environment. Even though the galaxy becomes quieter, the changes that occurred during its active phase leave lasting effects. Much of the original gas has already been consumed or expelled. The composition of the remaining material has been altered by the processes that took place earlier. Heavy elements produced by massive stars and supernovae are now mixed into the gas and dust that remain. The reduction in gas supply continues to influence the galaxy's behavior. As the available material decreases further, star formation slows even more. Eventually, the rate may become very low, approaching a level similar to or even lower than that of stable galaxies. At this point, the galaxy has fully transitioned out of its active phase. The fading of the galaxy is closely tied to this decline in star formation. Without a steady supply of new, bright stars, the overall luminosity decreases. The galaxy does not disappear, but it becomes less prominent. Its light is dominated by older stars, which emit less energy and have longer lifespans. This fading process is gradual and can take a long time. Even after star formation slows significantly, the stars that already exist continue to shine for millions or billions of years. The galaxy remains visible, but its character is very different from what it was during its peak activity. The quieter state is more stable and can be maintained for a long period. Without the intense processes that drive rapid change, the galaxy evolves more slowly. The remaining gas may continue to form stars at a low rate, but there is no longer the same sense of urgency or intensity. The absence of strong outflows also changes how the galaxy interacts with its surroundings. During the active phase, material was being pushed out into the surrounding space, affecting the environment beyond the galaxy. In the quieter state, this influence is reduced. The galaxy becomes more isolated in its behavior, with fewer large-scale interactions driven by internal activity. The internal balance of the galaxy improves as well. Energy input and gas motion become more moderate. The system moves closer to a steady state, where changes occur slowly and predictably. This is similar to what is seen in more stable galaxies, though the path taken to reach this state is very different. As the galaxy continues to age, the population of stars changes. Massive stars, which once dominated, are no longer present in large numbers. Instead, the galaxy is filled with older, longer-lived stars. These stars evolve at a slower pace and do not produce the same dramatic effects as their massive counterparts. The long-term fate is therefore defined by a transition from intensity to calm. The processes that once drove rapid change lose their strength as the fuel that supported them is used up. The galaxy settles into a quieter existence where activity continues but at a much lower level. The depletion of gas remains the key factor throughout this entire evolution. It sets the pace of change and determines how long the active phase can last. Once the gas is reduced to low levels, the conditions needed for high rates of star formation can no longer be sustained. This transformation is not unique, but in this case it is more extreme because of how quickly the gas was used. The rapid consumption during the active phase means that the transition to a quieter state also happens on a shorter timescale, compared to galaxies that evolve more slowly. The final state is one where the galaxy has stabilized, with reduced activity and a lower overall energy output. It continues to exist, shaped by the events of its past, but no longer defined by them. The intense processes that once dominated are replaced by steady, long-term evolution. The fading into a quieter state does not erase what came before. The structure, composition, and stellar population all carry the imprint of the earlier phase. The galaxy's history is written into its present condition, even as it moves forward into a more stable future. Over long periods, the remaining gas may become even more scarce. Star formation could continue to decline until it becomes almost negligible. At that point, the galaxy would be composed mostly of aging stars, with very little new activity. Why scientists call it horrific. Messier 82 earns this description not because of a single dramatic event, but because of everything happening at once, all the time. The conditions inside the galaxy are not occasional or isolated. They are constant and overlapping. At the core, there are continuous explosions. Massive stars form in large numbers and live short lives, ending as supernovae. These explosions do not happen one at a time, with long gaps in between. They occur repeatedly in different regions, creating an environment where shockwaves and energy are always present. The galaxy never gets a chance to settle. Alongside this, the radiation environment is extreme. High-energy emissions, including X-rays and gamma rays, fill the galaxy. Cosmic rays move through space, interacting with gas and dust. This radiation does not fade quickly. It remains intense because new sources are constantly being created. The result is a space where matter is continuously affected, altered, and broken down at the atomic and molecular level. Massive outflows add another layer to this system. Gas is not only being used to form stars, but is also being pushed out of the galaxy at very high speeds. These outflows carry energy, heat, and material far from the core. They stretch outward in large structures, showing that the effects of the internal activity are not confined. They extend far beyond the central regions. What makes it horrific in scientific terms is the combination of these factors. Explosions, radiation, and outflows are all happening together, feeding into each other. Each process strengthens the others. Supernovae increase radiation and drive outflows. Outflows remove gas and spread energy. Radiation alters the remaining material. There is no single moment where everything peaks and then stops. Instead, the galaxy exists in a continuous state of high-energy activity. It is not a one-time event. It is a sustained condition. The system is always active, always changing, and always intense. This ongoing nature is what sets it apart from more typical galactic behavior.